Hello everyone, in this lecture you will study about the number system that is used in the computer systems, and we are very well familiar with the basic number systems that we use in our daily life are decimal number systems, and we know that these numbers are used for counting a particular quantity or representing a particular amount. All right, so the number systems in the computer systems have different significance and applications, and there are a variety of the number systems in the computer systems that we use. The most familiar ones are the binary numbers, others are octals, hex numbers, and then we have ASCII characters. The decimal number systems has the base or the radix 10. All right, these different numbers have different applications in the computer systems. Usually the information is processed in the form of the binaries that are 1 and 0. All right, next we have the octal numbers. Octals or the hex numbers are the compact form of the binary numbers, and they are used for representing the addresses of the memory locations, and similarly ASCII characters are used for representing the alphanumeric characters or the symbolic or special characters of the keyboard. All these number systems have a special or specific basis associated to them. Let's say if we represent the radix or the base with r, then for the binary the radix or the base r is equal to 2. For the octal numbers we have radix is equal to 8, and for the hex it is equal to 16. All right, now let's study how the ranges of these different binary numbers are determined. So range of any particular number system is determined as r range is equal to 0 to r minus 1. So in case of the binary we have the range from 0 to 1. Only 0 and 1 are representable in the binaries. For octal numbers we have the range starting from 0 to 7. All right, so we can represent 0 to 7 numbers in octals. Similarly, for the hex numbers we have the range from 0 to 15, and in place of 15 we use the alphabet ELF. All right, we will see later on how we actually represent these numbers in the binary format as well. So in this way we have determined the ranges of the different numbers. Now let's have a look of these number systems in the form of their binary code. So let's say in case of the octal numbers we have the range of the numbers starting from 0 to 7. All right, so we can write it separated as 0 1 2 3 4 5 6 and then 7, and their binary code, and in form of binary numbers how many bits are required for representing a number. Let's see, if we use only 2 bits then we can determine the numbers that are representable with the 2 bits are 2 raised to power 2, which is equal to 4. So we can represent only 4 digits starting from 0 in 2 bits, that is equal to 0 0 0 1 1 0 and 1 1. No other combination of the 2 bit is available that has been missed over here. So we can see this is equal to 0, this is equal to 1, it is equal to 2, and then this is equal to 3. So when we have two number of bits, we have the range of the integers from 0 to 3. Now in case of the octals, we want to represent the numbers from 0 to 7, so we need more bits. Let's see, if we use the 3 bits, we can have 2 raised to power 3 is equal to 8. So in this way we can have the combination from 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, and then finally when all bits are on. These bits are actually the weighted sum. So we can map them. Let's select any of the combinations and see how these bits have been represented as the weighted sum. So let's take the example of 4. All right. So 1 0 0. This has the weight of 2 raised to power 0. This has the weight of 2 raised to power 1, and then this bit has the weight of 2 raised to power 2. And then we finally add all these weights. So 2 raised to power 0 is equal to 1 plus 2 raised to power 1 is equal to 2 plus 2 raised to power 2 is equal to 4. One thing to be noticed is that this weight is being multiplied with 0. This weight is being multiplied with 0, while this weight is being multiplied with 1. So when you will add up these weights, you will get 4 plus 0 plus 0. So in this way you can see how these octal numbers are represented in the binary forms. The same code for the hex numbers can also be generated, and we can see we have the range of hex starting from 0 to 1 2 3 4 5 6 7 8 9 A B C D E and then F, where A maps to 10, B maps to 11, C is actually 12, 13, 14 and then 15. Fine. So let's see how these binary codes for the hex numbers are generated. Since the range is from 0 to 15, that's why we will need at least 4 bits. 2 raised to power 4 is equal to 16, so that we can represent total 16 numbers of the hex using 4 bits. So the minimum number of the bits required for representing a hex digit is equal to 4. So let's see the binary codes for these hex numbers. That is equal to 0 0 0 0 when all bits are off. For 1 we will have 0 0 0 1, then 0 0 1 0, 0 0 1 1 and 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1, then 1 0 0, 1 0 0 1, 1 0 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, then 1 1 1 0, and finally we will have all bits on. And if you take now any of these combinations of the bits, you can verify it by using their weighted sums. Let's have an example of this. So we can have 1 1 0 0. This is 2 raised to power 0, 2 raised to power 1, 2 raised to power 2 and then 2 raised to power 3. So 0 multiplied by 2 raised to power 0 is equal to 0. This will also be equal to 0. 2 raised to power 2 4, 4 into 1 4 plus 2 raised to power 3 is equal to 8. So finally we will have 12. So in this way the hex numbers are assigned the binary equivalent. Now let's do the example where we will be converting any decimal number into different bases. For example, if we are given any decimal, any number in the base 10, so let's just be more specific. We represent any number in base 10 as the number is written, and then we use the parenthesis, and in the subscript you have to mention the base. So this is basically a decimal number. Fine. Now let's convert this decimal number into binary, and then into octal, and finally into hex. Then I will perform the reverse task where the hex, octal or a binary number will be converted into the decimal number. So let's start with the conversion of a decimal number into binary. The procedure is very simple. All you have to do is to take the LCM with a particular base in which you want to convert the given decimal number. So since I want to convert this decimal number into binary number whose base is equal to 2, that's why I will take its LCM with 2. So 2 2s are 4, and then 2 7s are 14. Remainder is equal to 0. Here you write the quotient, and here the remainder is written. Then 2 1s are 2, 2 3s are 6, and there you get the remainder 1. Similarly 2 6 are 12, and remainder is equal to 1. 2 3s are 6, remainder is equal to 0. So the last step is you will be dividing it by 2. So 2 2s are 1, and the remainder is equal to 1. Usually when the remainder is left, when the quotient is left is equal to 1, we are done. No further division is possible, so that's why we will start writing or from here, and we'll go upward. So I will start writing from the leftmost side, 1 1 0, then 1, then 1, and finally equal to 0. So in this way 54 is converted into the binary. Similarly, if you want to convert 54 into octal, what you need to do, you will divide it by 8 using the same procedure. So 54 divided by 8, eight 6 are 48, and the remainder is equal to 6. Now you can see clearly no further division is possible, so that's why 54 is equal to 66 in octal. 6 is a separate digit and 8 is a separate digit, so we will call it 66. Fine. Similarly, the same procedure will be done for converting this 54 into octal, into hex, whose base is equal to 16. So 16 3s are 48, and the remainder is equal to 6 again. So 54 is equal to 36 in hex. Here you can see I have taken an example of a number that has non-fractional parts, but we can also do the same for the fractional parts as well. So let's see if we were having a number 54.51. Fine. So how we can convert this 54.51 in binary? We will do the same for the non-fractional part, just like we did in the previous example, and all the values .51 will be multiplied by the base in which we want to convert. So we will multiply 0.51 by 2, and we will get 1.02. Now what is the next step? The next step is to write down I will just write it again, 110 This is for the 54. Then I will mention a point. We got 1.02. So I will write the non-fractional part after this decimal point, and then the rest of this amount will be again multiplied by 2. Again, when we will multiply 0.02 with 2, we will get 0.04. We will drop down this fractional part and we will write this 0 part here, and it depends on the amount of the precision we actually need in our example. You can keep continuing with the multiplication. Again, when you will multiply it by 2, you will get 0.08. So you will have 0 over here, and so on. So in this way, the fractional decimal numbers are converted into the binary. Similarly, for the 54.51 into octal, we will again write 66 point, and then 0.51 will be multiplied by 8. So 0.51 multiplied by 8 will result in 4.08. You will drop down this fractional part and you will just write it as 66.4, and then you will multiply 0.08 by 8. You will get 0.64. So you will write 0 over here, and then the remaining part is multiplied by 8 again. That gives us 5.12, and so on. In this way, you can actually, if you are interested in only 3 decimal places, you can just stop it here and write it like that. Fine. And I hope you can also do exactly for the hex numbers as well. So this was the one way of converting a binary number, a decimal numbers into the different bases, and I just mentioned the examples for each case individually. Let's see, is there any other way for converting a decimal number into hex or in the octal format? So I will consider the previous example again, where we had done or converted 54 that was in decimal into binary. So I can perform the direct conversion as well. If we are having the binary equivalent form of a decimal number, we can directly convert them into octal or hex. Let's see how. For the given combinations of the bits, we will start from the rightmost side and we will combine the 3 bits in case of the octals. So starting from the right hand side, we can combine these 3 bits, and then we can combine further 3 bits, and then we will find their decimal equivalent. So we know that 110 is actually equal to 6, and similarly 110 is equal to 6. And if you remember in the previous example, you can see 54 was equal to 66 in octal, so the resultant is true. Similarly, if you want to do it for converting into hex, all you need to do is what? You just have to combine the 4 bits now. So 110110. Since 4 bits are required for representing each hex digit, so that's why if you notice, so you have combined 4 bits from here. Now we need 4 bits, so we will append 2 zeros on the left hand side. Now we know that 0100 is actually equal to, this is equal to 0, this is equal to 2, this is equal to 4. So you will have this is equal to 6 and this is equal to 3, and the result is again same as we did in the previous example. I hope you are clear now how to convert any decimal number into the different bases. Fine. Now let's perform the reverse task, in which we are given the numbers in the different bases, like we are given in the binary, hex and octal, and we want to convert all these numbers into decimals. The procedure is very simple. Again, we will actually find their power series summation, and in this way we will be able to convert any given number into decimal. So starting from the binary combination, let's say we are given a binary combination as 1 1 0 0 1 0 1. If this binary number has non-fractional part, we will start from this LSB. This is actually called the least significant bit, or LSB most commonly. Similarly, this is called the most significant bit, or in other words MSB. As you will see, it has the lowest weight in the binary combination, and it will be having the highest weight as compared to the rest of the bits. That's why we call them LSB and MSB respectively. So starting from the rightmost bit, all you need to do is to multiply it with the power of 2, having the power starting from 0. Why the power of 2? As this number is in binary format. So what we will do, 1 plus 2, 0 multiplied by 2 raised to power 1, then 1 multiply by 2 raised to power 2, then 0 multiply by 2 raised to power 3, then 0 multiply by 2 raised to power 4, and then I will keep adding and multiply the numbers 2 raised to power 5, and finally 1 multiply by 2 raised to power 6. Once you will simplify this expression, you will get the decimal equivalent to 1 0 and 1. So this is equal to 101 in decimal. The procedure is very simple. Let's say we will do it now for the octal base conversion. All you just need to do is multiply the bits in the with their bases. All right, so if we are having a number in octal 4577, fine. So if you are having a number 4577, this is an octal number since none of the digit is greater than 8, and we want to convert it into decimal. What we will do, as this is in base 8, we will take its rightmost integer and multiply it with the power of 0, the base, and then starting from 0, then we will multiply again 8 raised to power 1, then 5 multiply by 8 raised to power 2 plus 4 multiply by 8 raised to power 3. All right, and if you simplify it, you will get 7. This will be equal to 7 plus 8 sevens are 56, then 16, 64 multiply by 5, 320, 8 raised to power 3 multiply by 4 is actually equal to 2048. Fine, and finally you will be just adding them up. So 320 plus 56 plus 7. Fine, this is equal to 2431. So this is actually the decimal representation of 4577. And similarly, if you are having a number in hex, let's see how does it work. AF11, this is in hex base 16, and we want to convert it into the decimal number again. What you need to do, you will again start with the LSB multiplied with the 16 power 0 plus 1 multiplied by 16 raised to power 1 plus F multiplied by 16 raised to power 2, then plus A multiplied by 16 raised to power 3. Now let's just simplify this expression. You will get this is equal to 1 plus 16 plus the decimal equivalent of F is equal to 15. So yeah, when you will multiply 16 square into 15, you will get 3840, and then 16 cube multiplied by A is equal to 10. So you will get 40960. When you will sum all these results, you will get answer is equal to 44817, which is equal to 44,817 in decimal. So we have done an example or multiple examples that were having non-fractional parts. Now I will just do a simple example where we will be having some fractional part as well, and you can see how does it work. So starting from I would like to prefer to do for the octal. So 17.441. Fine. So let's just convert this octal number into the decimal number. We will do the same procedure for the non-fractional part, and then we will do the fractional part as well. So we know that 17 multiplied by 8 raised to power 0 plus 1 multiplied by 8 raised to power 1. So we are done with the non-fractional part. Now what we do for the fractional part is we will again introduce the addition sign or plus sign, and then we will start multiplying with the negative powers of 8. So 4 multiply 8 raised to power minus 1 plus 4 multiplied by 8 raised to power minus 2, then plus 1 multiplied by 8 raised to power minus 2, and finally we will simplify this answer. So you will get 8 raised to power minus 2 multiplied by 1. This is equal to 0.015625, then plus, sorry, this is equal to minus 1 minus 2, and it is equal to minus 3. So let me just correct it. 8 raised to power minus 3, this is equal to 1.953125 into 10 raised to power minus 3 plus 8 raised to power minus 2 multiply by 4, and you will get 0.0625, then 4 multiply by 8 raised to power minus 1, this is equal to 0.5, then 7 plus 8. Fine. Now let's just add all these terms. You will get 8 plus 7 plus 0.5 plus 0.0625. Fine. Then plus 1.953125 into 110 raised to power minus 3, and you will get the resultant is equal to 15.5644 in decimal. Fine. So in this way you can see how we actually perform the convergence of the fractional parts. For more clarification, we can also do another example for the binary numbers. Let's just do it quickly. If we are having 101.001, so all we need to do is 1 multiplied by 2 raised to power 0 plus 0 multiplied by 2 raised to power 1 plus 1 multiplied by 2 raised to power 2, then plus 0 multiplied by 2 raised to power minus 1, 0 multiplied by 2 raised to power minus 1 plus 1 multiplied by sorry, minus, this is minus 2 and this is minus 3. Fine. So 2 raised to power 2, 4 plus 0 plus 1 plus 0 plus 0 plus 1 over 8, 1 over 8, which is equal to 0 0.125. Now let's just sum all these terms. You will get the resultant, which is equal to 5.125. So this is basically equal to the, this is the decimal representation of this fractional part. In this way we actually perform the conversions. I hope these much examples are enough for understanding the concept of the number systems conversions. Thank you for watching.